Atmospheric pressure is the pressure caused by the weight of the atmosphere. Atmospheric pressure is exerted on everything on Earth, including you. You cannot feel this pressure because the fluids inside your body also exert pressure, but you can measure it with a barometer.
Atmospheric pressure is the pressure caused by the weight of the atmosphere. Air pressure changes with altitude and can be measured with a mercury barometer. The height of the mercury in the tube indicates the atmospheric pressure in millimeters. If the atmospheric pressure increases, the air exerts more pressure on the mercury, causing it to rise in the glass tube. Thus, the mercury in the barometer rises with rising pressure. If the atmospheric pressure decreases, the pressure on the mercury also decreases. Some mercury will fall out of the tube and back into the container. Thus, the mercury in the barometer falls with falling pressure. Boyle's law. Boyle's law states that the volume of a fixed mass of gas varies inversely with pressure at constant temperature. As the volume increases, the pressure decreases. As the volume decreases, the pressure increases. Pressure is caused by the collisions of gas particles with the side of the container. With a large volume, the particles do not collide with the sides of the container very often, and the pressure is relatively low. When the volume decreases, the particles of the gas collide with the sides of the container more often. With more collisions, the pressure increases. Boyle's law states that the volume of a fixed mass of gas varies inversely with pressure at constant temperature. In other words, the smaller the volume, the higher the pressure. Equation for Boyle's law. This equation describes the relationship between the volume of a gas and its pressure at a constant temperature. As shown in the graph, as the volume increases, the pressure decreases. As the volume decreases, the pressure increases. The pressure of a gas times its volume is a constant. Charles's law. Charles's law states that the volume of a fixed mass of gas at constant pressure varies directly with the Kelvin temperature. As the temperature decreases, the volume decreases. As the temperature increases, the volume increases. Charles's law states that the volume of a fixed mass of gas at constant pressure varies directly with Kelvin temperature. Liquid nitrogen is very cold at 78 kelvins. When a balloon is placed in liquid nitrogen, the balloon shrinks. As the temperature decreases, the volume also decreases. When the balloon is removed from liquid nitrogen, the balloon returns to its original volume as the air warms the balloon to its original temperature. Equation for Charles's law. This equation describes the relationship between the volume of a gas and its temperature at a constant pressure. As shown in the graph, as the temperature increases, the volume increases. As the temperature decreases, the volume decreases. For a gas maintained at constant pressure, the ratio of the volume of the gas to its absolute temperature is a constant. Gay-Lussac's law regarding combining volumes of gases. Gay-Lussac's law of combining volumes of gases states that, at constant temperature and pressure, the volumes of gaseous reactants and products can be expressed as ratios of small whole numbers. In the early 1800s, Joseph Gay-Lussac studied the relationship between the volumes of gases involved in chemical reactions. He found that 1 volume of hydrogen gas reacts with 1 volume of chlorine gas to form 2 volumes of hydrogen chloride gas. No matter what volume of gases he used, the ratio of hydrogen and chlorine remained the same. Using Gay-Lussac's law of combining volumes of gases and Avogadro's law to find mole ratios. Based on Gay-Lussac's law of combining volumes of gases, we know that the volumes of gaseous reactants and products can be expressed as ratios of small whole numbers. Based on Avogadro's law, we know that these whole number ratios represent molar ratios. So if, at a constant temperature and pressure, 1 volume of hydrogen gas reacts completely with 1 volume of chlorine gas to produce 2 volumes of hydrogen chloride gas, we know that the mole ratio of the reactants is 1:1. Gay-Lussac's law of combining volumes of gases says that gaseous products and reactants have ratios that can be expressed as small whole numbers. So if, at a constant temperature and pressure, 1 volume of hydrogen gas reacts completely with 1 volume of chlorine gas to produce 2 volumes of hydrogen chloride gas, we know that the mole ratio of the reactants is 1:1. Gay-Lussac's law regarding pressure and temperature. Gay-Lussac's law regarding pressure and temperature states that the pressure of a fixed mass of gas at constant volume varies directly with the Kelvin temperature. As the temperature increases, the pressure increases. As the temperature decreases, the pressure decreases. As the temperature of a fixed mass of gas at constant volume increases, the pressure also increases. Gay-Lussac's law states that the temperature of a gas is directly related to the pressure of the gas. Equation for Gay-Lussac's law regarding pressure and temperature. This equation describes the relationship between the pressure of a gas and its temperature at a constant volume. As shown in the graph, as the temperature increases, the pressure increases. As the temperature decreases, the pressure decreases. For a gas maintained at constant volume, the ratio of the pressure of the gas to its absolute temperature is a constant.
Combined gas law. The combined gas law is the relationship between the pressure, volume, and temperature of a fixed amount of gas.
Let's combine these equations. One constant times another is still a constant. The combination of the three relationships is known as the combined gas law.
Equation for the combined gas law. The combined gas law describes the relationship between the pressure, volume, and absolute temperature of a fixed amount of gas. For a fixed quantity of a gas, the product of the pressure and the volume divided by the absolute temperature is a constant. Relating temperature and pressure. Given a constant volume of a gas, an increase in temperature will result in an increase in pressure. When the volume of a gas is kept constant, pressure increases with temperature. If a balloon is blown up as big as it gets, we have a situation with constant volume. If we then heat this balloon, the pressure in the balloon increases. If we heat the balloon too much, the pressure on the inside becomes more than the balloon can tolerate and it bursts. Ideal gas law. The ideal gas law describes the mathematical relationship between pressure, volume, temperature, and the number of moles of a gas. The ideal gas law is written as PV equals nRT. This stands for pressure times volume equals number of moles times the gas constant times the temperature. The gas constant is very important as it relates 4 measurable quantities: pressure, volume, temperature, and amount of gas. For example, if we take this constant volume box and add more gas to it, the pressure will increase. If instead we have a flexible container and add more gas, the box container will expand. The gas constant must have the units used by the other quantities in the equation. Some examples are R equals 8.314 liter kilopascals per mole Kelvin and 0.0821 liter atmospheres per mole Kelvin. Note that in both examples of gas constant, the pressure unit is different. This results in a different coefficient. Picking the right gas coefficient is important to make sure your units cancel out when doing calculations. Avogadro's law. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. If we filled balloons with the same volume of different gases, they would all contain equal numbers of molecules. But if we weighed each balloon, we would find that they did not have the same mass. We have the same number of molecules in each balloon, but the mass of the molecules in one balloon differs from the mass of the molecules in the other balloon. This is why in air, a balloon filled with hydrogen or helium rises, and a balloon filled with carbon dioxide sinks. Equation for the ideal gas law. This equation describes the relationship between the pressure, volume, temperature, and moles of a gas, assuming that the gas is an ideal gas. The ideal gas law can be derived from Boyle's law, Charles's law, and Avogadro's law. Boyle's law states that, at constant temperature, the pressure and the volume of a gas are inversely proportional to one another. Charles's law states that, at constant pressure, the volume of a gas is proportional to its absolute temperature. From Avogadro's law, it can be deduced that, at constant pressure and temperature, the volume of a gas is proportional to the moles of gas present. Because volume is proportional to the inverse of the pressure, to the absolute temperature, and to the number of moles of gas present, it follows that it must also be proportional to the product of these three quantities. To make this proportionality into an equation, we need to insert a constant. We refer to this constant as the ideal gas constant and represent it with the letter R. Now, if we multiply both sides of the equation by P and rearrange slightly, we get the ideal gas law expressed in its most common form. The pressure of a gas times its volume is equal to the number of moles of gas times the ideal gas constant times the absolute temperature of the gas. Absolute zero. Absolute zero is the temperature at which all molecular motion stops. 0 Kelvin on the Kelvin scale, or minus 273.16 degrees Celsius on the Celsius scale. It is the lowest temperature possible. If an ideal gas were cooled to absolute zero, it would have a volume of zero, and, if the pressure were held constant, the volume of this gas would increase at the same rate as the temperature. Dalton's law of partial pressures. Partial pressure refers to the pressure of each gas in a mixture. Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. Dalton's law states that the sum of the partial pressures of individual gases in a mixture equals the total pressure of the mixture. For example, in this container, we can measure a pressure exerted by the oxygen in the container. If we begin to add nitrogen to the mixture, the pressure begins to rise. When the addition of nitrogen is complete, the partial pressure from the nitrogen plus the partial pressure from the oxygen equals the total pressure of the system. Equation for Dalton's law of partial pressures. This equation describes the relationship between the total pressure of a mixture of gases and the partial pressures of each of the component gases. In a mixture of gases, the total pressure of the mixture is equal to the sum of the pressures of each individual gas alone. Equation for density and the ideal gas law. Use this equation to find the density of a gas given its molar mass, pressure, and temperature. We can derive an expression for the density of a gas beginning with the ideal gas law. The number of moles of the gas, represented by N in this equation, is equal to the mass of the gas divided by its molar mass. If we multiply both sides of the equation by the molar mass, we eliminate that quantity from the right side to get the equation shown here. Next, we divide both sides by the product of the pressure times the volume to give us this equation. We'll slide this one up to give us a bit more room. If we examine the right side of this equation, we note the mass of the gas on the top of the expression and its volume on the bottom. Mass divided by volume is density, so we can insert D in place of the mass over the volume. When we solve for D, we get the equation for density shown here. The density of a gas is equal to the product of its molar mass and its pressure divided by the product of the ideal gas constant and the absolute temperature. Comparing diffusion and effusion. Diffusion is the random movement of particles from an area where their concentration is high to an area where their concentration is low. Effusion is a process by which gas particles under pressure pass through a tiny opening.
Diffusion is the random mixing that occurs when two gases come into contact with each other. The random motion of gas particles causes the gases to mix. When the stopcock is opened, the lighter hydrogen molecules diffuse faster than heavier nitrogen and oxygen particles in air. Given enough time, the flasks will have exactly the same composition. Effusion is different from diffusion. When a gas effuses, it passes through a small hole in its container, being pushed by the pressure of the container. When this balloon ruptures, it contracts and pushes the air out of the balloon.
Graham's law of effusion. Graham's law states that the rates of effusion of gases at the same temperature and pressure are inversely proportional to the square roots of their molar masses. The speed of gas effusing through a small hole is dependent on the mass of the molecules. Lighter molecules move quickly and effuse much faster than heavier molecules. When the stopper is removed from this perfume flask, the lighter oxygen molecules inside effuse out much faster than the heavier perfume molecules. Also note, the molecules in the atmosphere also effuse into the flask. Equation for Graham's law of effusion. This equation describes the relationship between rates of effusion and molar masses of gases. The rate of effusion of gas A over the rate of effusion of gas B is equal to the square root of the molar mass of gas B over the square root of the molar mass of gas A. Properties of an ideal gas. An ideal gas is a hypothetical gas that fits all of the assumptions of the kinetic molecular theory of gases. The ideal gas law gives the relationship between the pressure, temperature, and volume of a gas. If the gas molecules are very small and do not interact strongly with each other, these predictions are accurate within a wide range of conditions. The first prediction of the ideal gas law is that pressure is directly proportional to temperature, if all other factors are equal. Similarly, volume is proportional to temperature if pressure is held constant. Finally, pressure and volume are inversely proportional at constant temperature. Ideal gas law. The ideal gas law describes the mathematical relationship between pressure, volume, temperature, and the number of moles of a gas. The ideal gas law is written as PV equals nRT. This stands for pressure times volume equals number of moles times the gas constant times the temperature. The gas constant is very important as it relates four measurable quantities: pressure, volume, temperature, and amount of gas. For example, if we take this constant volume box and add more gas to it, the pressure will increase. If instead we have a flexible container and add more gas, the box container will expand. The gas constant must have the units used by the other quantities in the equation. Some examples are R equals 8.314 liter kilopascals per mole Kelvin and 0.0821 liter atmospheres per mole Kelvin. Note that in both examples of gas constant, the pressure unit is different. Comparing real and ideal gases. An ideal gas is an imaginary gas whose particles are infinitely small and do not interact with each other. A real gas is a gas that does not behave completely like a hypothetical ideal gas because of the interactions between the gas molecules. An ideal gas behaves as described by the ideal gas equation PV equals nRT. There are several assumptions about the nature of a gas that are required for it to behave ideally. A key assumption is that the gas molecules occupy no volume. In a real gas, the molecules have a small but positive volume. Another important assumption is that kinetic energy is dependent on temperature. This means that the molecules are moving at a speed dependent on temperature. Real gases have molecules moving at a variety of speeds. Ideal gases collide like billiard balls and bounce off each other while maintaining their speed. They do not stick to each other or their container walls. Real gases occasionally stick to each other or the container walls. Ideal gas particles are always moving, but collisions that lead to sticking can cause real gas particles to violate this rule. Ideal gases do not attract or repel each other. Sometimes real gases do attract or repel each other.
Stoichiometry. Stoichiometry is the proportional relationship between amounts of product and reactant in a chemical reaction.
The stoichiometry of a reaction tells us the proportional ratios between reactants and products in a chemical reaction. It can be used to predict how many moles of product are formed in a reaction from a specified number of moles of reactant. For example, if we want to make nitrogen monoxide from ammonia and we have 4 moles of ammonia, we will need 5 moles of diatomic oxygen. We can also predict that 4 moles of nitrogen monoxide will be formed along with 6 moles of water. If we start with 136 grams of ammonia, however, we will have used 8 moles instead of 4 moles. We have doubled the number of moles. The stoichiometry of the reaction tells us that we will need to double the moles of the other reactants as well. Based on this number of moles, we expect that 240 grams of nitrogen monoxide will be produced.